Okay, for this problem, you're trying to make an optically active diether. And this particular thing, if the product is optically active, and if you notice it has two oxygens attached to adjacent carbons, really think about this coming from an epoxide. Because an epoxide can start out as optically active, and then a lot of the reactions on it cause the epoxide to stay optically active. And so you can actually get an optically active product. So when dealing with this, the product of opening of an epoxide typically is a nucleophile attached to a carbon, attached to a carbon, attached to an OH. Problem is here, we've got ourselves two OR groups, and neither one of them's an OH group. Well, that's where these two conditions come in. What sodium hydride does is it deprotonates alcohols to make alkoxides, and what methyl iodide does is basically it's just an SN2 electrophile. So we've got so either one of these things, these oxygens, could be coming from the epoxide oxygen, and the other one comes from the nucleophile. So let's take a look at this. If our epoxide is here, our conditions are adding acid and an alcohol to that epoxide. This MeOH is your nucleophile. And the nucleophile is specifically an OMe group from the alcohol. Now, you're adding this to the epoxide under acidic conditions. That means you're going to be adding it to the more substituted side. So if we take a look at our two carbons, this carbon and this carbon, we compare them. This carbon is the more substituted carbon. That means this OMe group came from here. And so that means this oxygen right here is the one that comes from the epoxide. And the sodium hydride, all it does, deprotonates the alcohol and then does the SN2 reaction. Now, to figure out what epoxide this comes from, you need to redraw this molecule so the OH and the nucleophile are anticoplanar to each other. So we already have the OH as a line going down. What we need to do then is draw the nucleophile, in this case the methoxy group, as a line going to the top of the page. And so when we draw this, I'm going to use this trick right here, line, line, wedge, wedge, dash, dash. The methoxy group started as a dash to the bottom of the page and ends up as a line to the top of the page, so that's 2 clicks clockwise. So the methyl group starts out as a wedge to the bottom of the page and goes 2 clicks, and it ends up being a dash to the bottom of the page. The propyl group starts out as a line to the top of the page and goes 2 clicks and ends up being a wedge to the bottom of the page. Now, it's a pretty straightforward manner of drawing the epoxide after this. The epoxide oxygen is going to the bottom of the screen, so therefore the epoxide is going to the bottom of the screen, just like that. And then you keep the wedges the same. The propyl group is a wedge. This propyl group is a wedge. And you keep the dashes the same. That methyl group's a dash. That methyl group's a dash. And so this is the epoxide you're looking for. And if you flip it upside down, that epoxide looks like that. And now it's just a matter of figuring out which of the answers match this. In this case, it's answer B.